Okay, so let me say a couple of words about the next homework. So the first question we have, so I've kind of teased about this a little bit, and so here's where we put our money where the mouth is. Give an example of R modules A, B, and C, where B is isomorphic to A, direct sum C, and a short exact sequence that actually does not split, right? So give me something concrete where this happens. Here's another one I'm kind of teased about. Show that if you have any exact sequence, no matter how long it is, that basically you can form this by splicing together suitable short exact sequences. So you can take short exact sequences and kind of splice them together to make this. My splicing is a little bit undefined here, but we'll play around with this and see what you can get. And let me know if you need any help. Number 3 is a terribly fun problem, I think. Let F be a field and V a vector space of countably infinite dimension over F. So you might think of, a countable direct sum of a countably infinite direct sum of, say, real numbers. So let R be the homomorphisms from B to B, and this is a ring with identity, with multiplication given by function composition, right? Because when you compose 2 functions from B to B, you get a new function from B to B. The identity function is the identity, et cetera, et cetera. Show that as a left module over itself, R is isomorphic to n copies of R for every possible number, right? So that ought to anger up the blood a little bit, because now you have a free module, say R, that is isomorphic to R sum R, which is isomorphic to R sum R, et cetera, et cetera. So this is a very interesting example to show that in some weird cases, you do not necessarily have the same size basis, right? Actually, the big hump in this is going from R as isomorphic to R sum R. Once you can do that, the rest follows by induction very easily, right? So anyway, think about this. This is a fun one. Finally, I'm going to define injective and projective very soon in this class, but I give you this is in red here is the definition of injective. If you have a one-to-one map, these are all R module homomorphisms from A to B, and an R module homomorphism from A to I, then there exists an H that completes the diagram. That is, when you do G and H, it's the same as F. We say that I is injective if it's got this property. Show that the following conditions on an R module I are equivalent. And for the time being, you may assume without proof that any R module can be embedded inside an injective R module. You might need that for the implication here. I'm going to do, there's a dual mirror image of this, if you will, called a notion called projective modules, and I'm going to prove the similar theorem from that. That might help you get the idea. Any questions on that? So let us stop sharing. Okay. So the last time we were talking about free modules, and I gave you the following theorem, which I will think, and we will go through the proof of it. So let me recall for you. If R is right, what else? The unitary R module. Following are equivalent. One, F has a non-leaky basis. Two, F is the internal direct sum of a family of cyclic R modules each of which is isomorphic to R. Uh, the three, F is isomorphic to, that's kind of an external direct sum PL. But actually, this is one of my favorites because this means that any free module is actually, all you have to do to understand the free module is know how many copies of R you need, and that's it, which is kind of cool. Or, there exists a non-empty set and a function out of max into F such that, given any R module M, and function from X into M, there exists a unique R module homomorphism F bar from F to M such that and this is the old thing that probably you're intuitively in linear algebra. Basically what it says is if you have a homomorphism whose domain is a free module, all you got to do is tell the basis where to go, and that completely determines the homomorphism, right? Uniquely. So this is sort of a universal mapping problem that it solves. This is a function. This is kind of this canonical thing. So let's set about proving this. Okay, how about one implies two? So suppose you have a non-empty basis. I claim that if you have a basis, then it has to be the internal direct sum of some number of copies. So let X be basis of F. By the way, let me point out something. I say non-empty in parts 1 and 4. If you allow the basis to be the empty set, then the module is 0 and this all fall. This is actually very true if you have the empty set as a basis and F is a 0 module. So let X be our non-empty basis of F. So what do we know? We know that since X is basis, it spans F. So the submodule generated by X equals F. And so that's one of the things we need for the internal direct sum. What this really says is everything that you can find in F is some finite linear combination of the elements of this basis, right? Because this is exactly the module generated by set X, right? Really the burden here is to show that this set X, or I'm sorry, that you also get that it's a direct sum. So, or that is, we, direct. Now, if you recall, we have a characterization of what it means for the sum to be direct. So let's suppose not, then there exists R and Ri in, I'm gonna go this a little bit here. Then there's this M in Rx intersect the sum So I claim that these different cyclic submodules, these RXIs here, all satisfy what we need for correctness here. If not, we can find something that lives both in RX and what's generated by the stuff that's not equal to X in the basis, right? But then we have a relation of this form. And R not zero, then we set X is linearly. Because of course, bringing this up the other side gives you a non-trivial relation on the elements of the X, which we claim is a basis. All right, everybody okay with that? You know, I'm really gonna leave this as an exercise because if you have this as the internal direct sum, it's certainly an external direct sum. Just abstractly take your pieces that are the direct sum and do it this way. Notice that by hypothesis, each element of the internal direct sum, these cyclic R modules are each isomorphic to R, right? Everybody okay with that? 2 implies 3 is the easy one. How about 3 implies 4? The 3 implies 4. We'll let F be isomorphic to some direct sum number of copies of R, which I'm going to actually index by I. With each Ri isomorphic R via, I'm going to give you a function here. VI Okay, and of course, what we want to do is we want to sort of build this. We want to build a set X and this iota function that makes this work. Well, here's what we have. So for every I, diagram. Say Ri goes to R, VI, and Ri, of course, includes into And by the way, once we have that situation, we get this map right here, don't we? This is one of the properties of direct sum. So I'm going to define Well, we'll define this set X by this collection of xi such that, how am I picking this xi? This is an isomorphism here. And the generator of R is an R module is 1. So what I'm going to do is I'm just going to pick each xi from the respective Ri that goes to 1. So essentially this is just the generator of Ri. And that's what I'm doing. I'm cherry picking. I know that I've got this big direct sum of Ri. I'm just cherry picking all the generators of each separate Ri, right? And I'm going to grab them together, bundle them up, put them in the set X. And our function iota x into Ri. So this is of course part of the setup here. Our function is assigns each its the corresponding, say, so for example, xi might go to ei. Yeah, by the way, I'm going to use this notation later. When you have a direct sum of some number of copies of R, are you familiar with the notation? So let me kind of take a little aside here. If I have the direct sum of R in some index set, and let's say that J is in this index set, then EJ is, well, it's an element of this direct sum, so it's xi, where xi is equal to 0 if I is not equal to j, and 1 if I equals j. All right, so this is like kind of a standard basis, if you will, for Rn when you kind of on your output here. But what we're going to do is we're going to assign each x the xi and the ith coordinate. That is the cyclic generator of that coordinate. And you can pass to f by whatever this isomorphism is, if you want to do it a little bit more generally. And so, that is to say, iota of xi is iota I of xi from my previous diagram here, which now I kind of erased. Okay. Now let's say, now suppose you have some function from x to here, right? Some function. Now, let me put some notation in here to kind of help us out. Let's suppose this function is corresponds to the rule F of xi is mi in M. So basically, we pick this arbitrary xi goes to mi in M. Then the homomorphism F bar from F M is F bar of sum Ri iota I xi is equal to Ri. So basically, the RIs are fixed. It just reads where each one of these iota i's goes. It goes to, well, where it has to go. We want to send that to MI to make a diagram. This is easy to check. It's a homomorphism. Easy to check if this is a homomorphism. And uniqueness. Unique. Follows these two. Because to make that set map work, you have to take each of these to M, right? And once you've done that, it determines everything, because these iota i's, they basically comprise everything in here can be written as a sum of this. And so once you've told these where to go, the rest, the homomorphism takes care of everything else. Okay, any questions? Okay, the last thing I want to do is formalize one. And so what I'm going to do is I'm going to kind of make a bold claim here. Suppose we have a situation, so there exists iota from x into f, such that for all f from x to m function, there exists unique f bar from f to m, such that f bar iota. And our goal here is to show that f has a basis, right? So what I'm going to do is consider of x. This is a subset of f, right? Because iota is just a function that pushes x up into there. So I'm going to claim that this image, this ix is a basis. How are we going to go about that? Well, I'm going to do a couple of diagrams here. Now, for I of x to be a basis, I got to have two things going on. It's got to span, so it's going to generate the whole thing, and it's got to be linearly independent. All right, so the first thing I'm going to do is I'm going to claim the spans. So let's consider. Generated by be everything, right? Any ideas how we can show this is everything? The way I think to go about proving this is to pick your module sagaciously, right? So here we have our f. Now, here's what I'm gonna do. I'm gonna let F, well, here's the way I want this function to work. I've got a lot of freedom with my function. I'm gonna let F max M be defined this way. F of so basically what I'm doing is, this is F modulo all I of X. So what I'm gonna do is I'm just gonna take this off to the zero element over here, right? Now, can anybody give me an example of a homomorphism? So when I go up here, this goes to some xi, and here you're going to zero, right? So can anybody give me an example of a homomorphism here that will make the diagram for you? Right, the zero homomorphism will make the diagram here, but I can think of another one.
Oh, yeah.
Right, the projection. So notice that F bar from F mod IX given by F bar of alpha is alpha plus IX makes diagram. Correct. But so does zero. Right? By uniqueness, these have to be the same homomorphism. So, well, we call this G bar. So notice that F bar of the G bar, which is the zero homomorphism by uniqueness. So that means this has to be the zero module, right? So it stands. Okay. Okay, we also now need to, this is linearly independent. So let's go X is linearly independent. Well, suppose we have the following relation here. Yes. R1 xi1 plus R2 by 2 plus R n xin. Suppose that you have this relation being zero, where is there
Is in iota in X to show iota in X the thing that you want that is linear independent.
what's that mean?
And to show iota X is in the thing that you want to show that is linear independent.
Right. Oh, okay. Yeah. Thank you. I see what you mean. Yeah. We need to show that that's linearly independent set. Yeah, X by itself is just some abstract set. So suppose we have this relation here with the Ri's and R and xik with an X. So this is just some finite collection of elements out of X. Now, here, what I want to do is I'm going to form, anybody know, so here I form this submodule or this module to make it work. Anybody know what I do want to form this time? Because I'm going to do the same trick, but I'm going to have to
quotient, cyclic module, some copies of.
Yeah, so you want, I don't think I want a quotient here. The quotient here works very nice for showing the spanning. What I'm gonna do here is I'm going to let M I'm gonna have one copy of R. So this is like a little direct sum of N copies of R, and the N just sort of matches how many of these I have here. And I'm going to define F from X into M via the following. F of X sub alpha is E sub J. If alpha equals I sub J for some J between 1 and N. So in other words, if I stumble upon I1, this is just E1, so it'll be 1, 0, 0, right? And if I stumble across I2, this will be 0, 2. And for every other thing, so every element in X that isn't one of these Xi's here, I've killed. They all go to 0. And this one goes to 1, 0, 0, 0. This one goes to 0, 1, 0, 0. And this goes to 0, 0, 0 up to 1, right? Now, right. The induced homomorphism F bar from F into M has the property that F out of Xij is equal to EJ. So in particular, if you expand along this, then F of R1 and I guess I should have iOtis here. Probably, yeah, my apologies here. I really should have iOtis in front of these X's as per Pedro's correction earlier. There we go. Yeah. This should actually be, well, by the commutativity of the diagram, this actually needs to be 0. Right? And the reason is because this linear combination is 0, right? I mean, this is just a big fat fancy way of writing 0. But at the same time, our rule says that this is R1, R2, Rn as an element of, right? And this implies that R1, R2, Rn. And so this relation is that all R's have to be 0, and so it's linearly independent, and it's claimed as a basis. And again, just for fun, and if you're incredibly bored, go through and prove this where X is the empty set. It won't take you very long. Okay. Let me give you a corollary. Give you this last time, I think. And this is, I put a little star next to this. I really dig this corollary. And it actually illustrates why I think I kind of gave you a little taste of this last time. This is why I like direct sums more than direct products, because they are They control everything in a certain sense. M is a unitary homomorphic. Then R is, I'm sorry, then M is the homomorphic image. A free model. And this is actually kind of, if you're interested in the theory and range of computational commutative algebra, this is another important kind of offshoot of this. And if M is finitely generated, then the free module can be chosen. So, okay, so let me prove this correlate really quick. Okay, so let M be our R module. And let X be a generating set. Okay. Generating set, and then we'll assume it's non-empty, so I don't have to go back and silly stuff. Of course, any module has a generating set. You could take X to be all the module. That's incredibly inefficient, but it's there, right? So what do? Well, and let F be free on X. So notice that the number of copies of R are one-to-one correspondence with, there should be some crazy Greek letter here, a one-to-one correspondence with the elements of lambda, right? Where F of xi is xi, right? So I've just basically, I've sort of excised the generating set, just put it out separately here. Right. So notice that F bar of, and I don't really need an iota here because of the way I've set this up, xi is xi. Well, actually, here's what the iota is. Let me make it, I will put those iotas, xj. Right, so this is the way the iota here works. So let me. So there's a homomorphism that goes from the free module into M. I don't have to check this as a homomorphism because that's what the theorem said. I know this is homomorphism. The only thing I have to really check about this is the fact that it's surjective. Right? Anybody tell me why this has to be surjective?
The XI are generating set.
That's right. So notice that for all I in the index set, each xi is an image of that bar. Right? Because there it is right there. Right? Each one of these elements is in the image. Therefore, what's generated by X, which is F, or I'm sorry, which is M, is contained in the image of F bar. Therefore, horizontally. So that's super cool, right? Because any R module that you have is a homomorphic image. So, you know, for example, as I pointed out, the real numbers is an abelian group. It is the homomorphic image of some. So there's a onto homomorphism from some appropriately large number of copies of Z. So in particular, R is isomorphic to a large number of copies of Z, quotient out by some submodule B. This is certainly very complicated, right? And that index set has to be uncountable. Okay, any questions on that? All right, let me prove a theorem here. Any questions on this so far? I'm gonna specialize for a little bit. I'm gonna do about all the linear algebra. So this is gonna look like linear algebra, only gonna be over a division ring. I'm gonna do kind of a classic here. Lemma. 6 point something else. 655. A maximal linearly independent subset of B, a vector space over the division ring. Is a basis. Okay, well, somebody would criticize my lemma a little bit, how it might make you feel happy, but a little empty. Yeah,
I mean, the vectors of space are over the field, right?
yeah, I'm gonna do a vector space over division ring, right? So,
Module, the module, right?
yeah, well, so our definition of a vector space actually, and although practically I will concentrate most on the field, so our definition of a vector space is actually a module over a division ring, right? So it's a left module over a division ring. So I'm gonna do this in slightly more general.
So we call it a left vector space or something like that.
Yeah, so I should say, left vector space. Here's the problem. What this lemma says is, if you have a maximal linearly independent set, then it has to be basis. What it doesn't tell you is, does maximal linearly independent set actually exist or not, right? So, but let me just go with this now. So, so suppose this set is linearly independent subset of B, and is maximal. So what this means, let me make it absolutely clear that word. So if you have another subset of B that properly contains it, then this means Y is linearly dependent. Right? So that's what it means to be. So, what do I need for this set X to be a basis? I need two things, be linearly independent. Lucky me, right? No problem there, it's already linear. And I need it to span, right? So it suffices to show X spans V. Okay. Well, to this end, let's suppose W span X, and suppose there exists something alpha and D that's not in W. Right? Well, let me point out that alpha, there's no way it's an X, right? So if you look at alpha unit X, this must be linearly dependent. That actually has to be, because it's a set that properly contains X, since alpha is not in. So by the maximality of X, this has to be a linearly dependent set. Well, that means there exists D, D1, D2, DK in the division ring such that D alpha plus D1 X1 plus DK XK is equal to 0, right? And let me point out that D is not equal to 0, right? Because or we can assume that, because if D was 0, then that forces all the rest of these to be 0, right? And let me excise that, of course. Well, this means that D alpha is equal to negative D1 X1, negative D2 X2, negative DN or DK X2. And because of the fact that D is a division ring and D is not 0, I've got an inverse. So I can hit this thing on this side with D inverse and obtain alpha is minus D inverse D1 X1 minus D inverse D2 X2 minus D inverse DK XK. And of course, this side of the equation is in W. So I obtain alpha is in W, which is a contradiction. So X is a basis. Okay, any questions? So let me give you the last theorem that we will prove next time. I'm going to make this, I'm going to turn that frown upside down. I'm going to make this happy because I'm going to finish this up. So here's a theorem that probably looks very familiar. 6, 5, 6. Every vector space, well, every vector space over a division of B basis. So therefore it's free. And in fact, this probably looks familiar too. In fact, every linearly independent subset of B is contained in the basis. That is to say, you've got that old linear algebra theorem over the division ring, you can expand any linearly independent set to a basis. And it's crucial that the elements that are from the division ring are all invertible. Because we've seen this is not true in precision. So we will discuss this more next time. Any questions? Questions? Well.